Hello, and welcome to this presentation about collective work that's performed in the SNOW project. My name is Willeke van Vught, and today I will explain how we enabled competence assessment on an autonomous system using a knowledge graph. In previous presentation, my colleagues gave an introduction to the SNOW program, the hybrid AI approach we take, and the SNOW use case we will use. In this presentation, I will focus on a part of the knowledge base and the symbolic reasoning, to introduce and explain the ontology we use for self-assessment in the real world. In the SNOW use case, a firefighting team arrives at a villa where the living room is on fire. While the team is preparing to go in, Spot can be sent first to search and rescue possible victims. The main question we want to answer for the autonomous system in this use case is, am I competent to execute the given task in the environment it should be executed in? To answer this question, the system needs to be able to assess its own competence, and this is based on the many hard and software components it's made of. So in this image I show you a small part of the component Spot is made of, but it shows the object recognition part. So as you can see here, Spot might think, oh, I want to use my image recognition algorithm because its performance is very good under normal circumstances. But because the room is full of smoke, the image quality is very poor, and therefore the image recognition output is poor as well. So in this case, while it's searching for humans in a smoky room, this image recognition component might not be the most sufficient component to use. But it might, for example, use an alternative approach, namely use speech interaction to check if there are humans responding in the room it's searching in. So in this case, Spot can say, okay, I'm fairly competent using my speech interaction for this task. To make an autonomous system be able to reason like this, it needs to be aware of its own capabilities. So therefore, we created this general process model that can describe the components of a system and the configuration they can be in. So the model is shown on this slide, and let me take a laser pointer. So what you see here is that we have a process, which can be a hardware or a software process of a system. It has a required input, which is often a unit, and it has an output it creates with another unit. So the relation between the required input of a process and its output is called a functional requirement in this model. You also see that we have something like health state in here, so the health state of a process, which means, well, in this case, if the process is working or not, so if it can be part of an actual configuration. You also see that we have some qualities of unit. So here we can, well, for example, we can measure the input quality of that image, and we can measure the output quality of the object detector. And each unit might have its own properties that are very typical for that unit. So we modeled this in Kraken, and let's see. So we modeled entities, which are these purple squares. We modeled attributes, so these are these blue ovals. And we modeled relations, which are these green diamonds. So as we describe each component of the system via this model, we can also link components, because as you see, like, each component is described in a similar kind of way. And if the output of one component matches the input requirement of another one, we can create a realizing relation, which means that this output unit can realize the required input for this process. And in this way, we can link the components together and create the configurations. As you might have noticed, the realizing relation is dashed, and this means that this is actually a rule that's executed in the knowledge base. So this is an automated process that links these output units to these input units. So therefore, it's kind of resilience. If you add extra processes, it should be able to link it to the current processes as it goes. The advances of this general process model is that creating and expanding this component ontology for an autonomous system can be partly automized since, well, it's built in a consistent fashion. So here I want to show an example of part of the configuration of Spot using this process model. So let me take my pointer again. As you might have noticed, we've modeled 3 processes here. So the object tracker, the object detector, and an RGB camera. They are all linked together, and this is why we call this part of the configuration. And I will go through this, but then starting from the right. So as we might want an output of tracked objects with a, well, in this case, a label consistency of 0.8, we can check what components we need and which, well, how this quality came about. So as you might notice, we need an object tracker because it's the output of the object tracker. And on its turn, it needs an object detection as an input with a certain property, namely a class label via a ROS message. Well, luckily, our object detector can deliver such a thing. So our object detector delivers these object detections that are required with this class label via this ROS message. So therefore, this realizing relation is valid. And actually, so the confidence is also pretty good of this output. Well, and the same accounts for the object detector, which needs an RGB image. Well, and this RGB image is outputted by the RGB camera in the correct spectrum, which is also a very fine contrast and brightness. And on its turn, the RGB camera needs light. So this is a chain starting from the input of the first sensors to an output Spot can give, for example, when it needs to track objects in a villa. So as they are all linked together via this realizing relation, since the input and the outputs of these different processes are matching, and since the health state of each of these components is true, so they are all working correctly, this can be seen as part of a configuration of Spot that it can currently use with these kind of quality performances. So this shows that Spot can use the knowledge model together with the measured data, namely the quality measures and the health state measures, to reason about its competence in the current environment. So as mentioned briefly before, the actual process that's happening here is, for example, in this case, from an RGB image which serves as an input to the object detector, which is the executor, which outputs an object detection. And we can even get one level higher and say, no, the real process happening here is, for example, this process, which says that which takes an RGB image as input and uses 2 executors, namely the object detection and the object tracker, to create the tracked objects. So as we reason about this in this way, we can eliminate some data in this reasoning process. And in this case, we can reason a bit faster with less complex models while these relations are verified by the underlying slightly more complex model. And actually at the highest level, we can even say, okay, but the real process happening here is from the light that Spot gets as an input with a certain quality. It uses 3 processes, namely the camera, the object detector, and the object tracker, to actually get the tracked object with a certain consistency. So using this, we can reason about these high-level processes while all these underlying elements and processes are validated by the underlying process model. So this model is implemented in Gakken, where we modeled all components of our system and their functional requirements. We also trained a model about the performance of all the components of the system in different environmental conditions. So as you can see here, in a very smoky and a very dark condition, it cannot detect humans, as well as in a very clear or less smoky environment. And since we can sense the environment and we know the task to be executed, we can combine this knowledge in the ontology and using the process model as I just explained to reason about the current competence of the system. Now let's go back to the use case to show you how we can use this model in the firefighting example. So as you might remember from the start of this presentation, we were on a firefighting use case where the living room of the villa was caught on fire and the fire brigade was asked to help. And while they are getting ready to go in, Spot will be sent first to do some first search and rescue actions. And Spot was considering, okay, am I competent to do this task? So while it gets the task, it reasons about its non-performance, the environment it will be executed in, the actual task it has to execute, and combine its knowledge in the knowledge graph where it can reason about its competence using its performance model. Well, and in the best case, Spot will says, yes, I am competent, Roger, I will do it, and it's off. But actually, in a less ideal case, Spot thinks about this and thinks, okay, but let me get my pointer again. These smoky rooms might be tricky because I know that in smoky rooms my object detector performs not as well as I want it to. So it might say, okay, I will do it, but be aware that my performance is low, well, 20% in this case, for assessing persons in a smoky room. So the commander gets this message and it says, okay, well, maybe you can start by searching the rooms that are probably not smoking, because in his experience, Spot is very good in non-smoky rooms. And they will catch up, and as they go, they will start with the smoky rooms. So then Spot gets this message. It thinks about, okay, well, if I should do that, I will start a left-hand search and starting with the parent bedroom. And while it reasons about the performance then, it says, well, now I expect my performance to be very high, namely 0.8%. So it accepts the task, it says Roger, and it will go help extinguish the fire and search and rescue the victims. So to recap, we developed a general process model to describe the parts of a system and the system as a whole in a configuration. The autonomous system can use this model to reason about its performance in real time in the real environment given a task. And using this information, it can report the performance back to the user. So for example, in the use case I showed you where the autonomous system reasoned that in smoky environment its performance is very low, while in non-smoky environment its performance can be very high to detect humans. But it can also reason about alternative configurations, and that's the part I showed you in the beginning of the presentation, where it might reason that it could use speech recognition to detect if there are humans in a room better than the object detector if the room is very smoky. So the system can combine this knowledge in the knowledge graph and can reason about its performance in real time in the open world. This concludes my presentation. Thank you for your attention.